Okay, everybody, what we're going to be covering today, this is from chapter 3. It's called Graphing Inequalities with Intersections. I'm going to be reviewing how to graph inequalities, but then we're going to go a little further. We're going to graph quadratic, which is x squared, and absolute value inequalities. Remember, inequalities are less than, greater than, or equal to, with shading. So what I do, guys, is I kind of give you a little quick scenario of how to graph it with shading. So the very first thing we're going to do is we're going to graph the function. Now let's do this. Let's just review real quick. And it's the same concept for more difficult ones, which we're going to do in a little bit. But I'm just going to review from IM1. This is a while ago. How to graph inequalities. This very first step that you're going to do is you're going to graph whatever function it is. So 2x plus 2, you're going to pretend this is an equal sign. So you're going to go up 2, and then your slope is up 2 over 1, and so on. This is a solid line because it's equal to. Remember, if it was like this, if it was dotted, if it was not equal to, it would be a dotted line. Okay, but it's not. The original question that I just did was equal to, so it's solid. That means that you can have a point that lies on this line. Second thing is, you guys are probably thought if it's greater than, you shade up. If it's less than, you shade below. That's fine. But now I'm going to be teaching you how to shade it a little differently, because when you have quadratics and absolute value, you're not shading up or down. It doesn't work like that. So the very second step on the note says pick a test coordinate. The easiest test coordinate is usually 0, 0 right here. Now plug this coordinate, which is 0 into the x and 0 into the y. Let's simplify this. If I plug a 0 into the y, I have 0 is greater than or equal to 2 times 0 plus 2. 0 is greater than or equal to 2. This is an incorrect statement. So if the statement was true, I would shade where this is. I would shade below now. But this is not true, so I do not want to include this point in my data set. So I'm going to shade above, which is not where this test coordinate is. Now that's the concept of this. We are going to graph now some examples. But before we do any examples, let's take something very simple and let's relate it to the steps. First, let's graph this y. Let's just pretend this is y equals x squared. It's going to look something like this. But it's not equals, it's greater than. So I'm going to make it dotted. It's going to be a dotted line. All right, the dotted function. Next thing, I'm going to pick a test coordinate. Now, sometimes 0, 0 you will not be able to use, because that's this graph contains 0, 0. And you can't shade above or below that. So choose another coordinate that's easy to use. 0, 1, let's say, is right here. Let's use 0, 1. You can technically use any test coordinate, but 0, 0 or 1, 0 or 0, 1 is usually the easiest one. Now let's plug a 0 into the x, a 1 into the y, and see if this is a true statement. I'm going to plug this 1 into the y. 1 is greater than 0 squared. This is a true statement. So therefore, I'm going to shade inside, because it contains that test coordinate, because that test coordinate makes it true. If this test coordinate was not true, then I would shade on the outside, and all of this would be shaded. Nothing on the inside would be shaded. Okay. Now, what we're going to be doing is we are actually going to be graphing a system. System is when you have two or more functions or graphs on an XY coordinate plane. I'm going to graph these two systems. Now the reason why in the notes I have it kind of looking weird where I say graph these and I draw like two arrows coming down and it says on one coordinate plane, because I was originally going to have you graph each one of those individually, but since this is STEM, because if this is just Math 3, I would have had you graph each one individually, and then the next assignment, I would have you do it on the same graph. But since this is STEM, I just went ahead and skipped the first assignment and said, let's just graph everything on the same graph. So I'm going to graph this first. All right, so I'm going to pretend this is an equal sign. My vertex is -2, -3. This is an absolute value, and my shape is an invisible 1. So I'm going to go up 1, over 1, up 1, over 1. And since absolute value is linear, it would continue this forever. This is equal to, so it's going to be a solid line. And I have to do a test coordinate. I'm going to use 0, 0. I could use 0, 0 because it does not lie on this. So I'm going to choose a test coordinate of 0, 0 and see if this statement is true. If I plug a 0 into both of these, I'm going to do this in my head. 0 is greater than 0. Absolute value of 0 plus 2 is 2 minus 3. 0 is greater than -1. That is a true statement. This test coordinate made this statement true, so I'm going to shade inside. Okay, that's this. Now what I'm going to do is I'm going to graph, look at the other one that it's pointed to. The other one that it's pointed to where it says graph on the same graph, which is a quadratic inequality. So first off, I'm going to graph the quadratic. Let's do this. Let's change this into factored form first. It makes it a little easier. Y is less than or equal to x minus 3 times x plus 2. That means I'm going to have roots at -2 and positive, let's say 1, 2, 3. My axis of symmetry, which is going to be the same as my x coordinate from my vertex, is going to be, it's going to be what? I'm going to go back 3. It's going to be 1/2. And I got to figure out how far down I would go down on my 1, 2. All right, so it's going to be 1/2. So my vertex is going to be 1/2 on my x. If I plug a 0.5, I'm just going to do this on my calculator real quick. I'm going to have 0.5 minus 3 times 0.5 plus 2. And I get a -6.25. So 1/2, -6.25 is down here. My shape initially is 1. So I go up 1, over 1, up 1, over 1. All right, so it's going to look something like this. It's going to be solid. And my x-intercept is going to be a -6. All right, and then I have to choose a test coordinate. Look, 0, 0 is super, super easy to use. Super easy to use. So I'm going to use 0, 0 and see if this is a true statement. Y is less than 0 minus 3 is -3. 0 plus 2 is 2. I'm sorry, not y. 0 is less than -6. 0 is less than or equal to -6. This is not a true statement. So look, I would shade below because I don't want to include that. And if I shaded in here, it would include that. So look, I would shade below. Now, these two graphs are shaded. But the question is, what is the overlapping region? Or it's also called the feasible region. The feasible region is where both graphs overlap in their shading. There's no overlapping between this quadratic and this absolute value. So there is no feasible region. That means there is no solution. So the very first example, the answer is no solution. Why? Because there's no overlapping in the graphs. All right, let's do the blue in the notes. The blue are two example questions. The very first one is y is greater than or equal to x squared. All right. This is going to be a solid quadratic. Now, I'm not going to use 0, 0. I'm going to use another test coordinate. Let's use 0, 1. 0 for your x, 1 for your y. 1 is greater than or equal to 0 squared, which is 0. This is a true statement, so I'm going to shade inside. Okay, that's the first one. The second one on the x looks a little weird. It's it says x squared plus y minus 2 squared is less than or equal to 16. Oh, wait. What kind of graph is this? You should understand this is not a quadratic. It's not an absolute value. It's actually a circle. Remember, whenever you have x squared plus y squared equals r squared, that's a circle. Okay, how do we graph that? Well, let's just pretend it equals 16. Instead of it's less than or equal to 16, let's just pretend it's equal 16 and graph it normal right now. My center would be 0 and positive 2. 0, 2 right here. Here's my center. All right, and then my radius is equal to the square root of 16, which is 4. So that means I'm going to go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right. Now, let's go ahead and graph this. This is a solid circle because it's equal to 16. Okay, so my graph is either going to be shaded on the outside or shaded inside in the circle. Well, let's use, this is a pretty messed up circle. I know, but whatever. Let's use this testing point as 0, 0. Let's plug it back into the equation. 0 squared is 0 plus y plus 2. 0 minus 2 squared is negative 2. Negative 2 squared is 4. Is less than or equal to 16. 4 is less than or equal to 16. This is a true statement, so I would include this in my data set. But look. First off, I'm going to extend my quadratic, and you'll see why I'm doing this in a second. And technically, this is graphed. This is shaded up, 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 up. Okay, now if this quadratic wasn't here, here's my 0, 0. I would shade inside my circle and be done. Okay, so technically, the inside of my circle is shaded, but all I care about, watch, is where they overlap. So nothing starts overlapping. I'm not shading inside here until I get to here. All of this is overlapping with the inside of my circle Remember, I want the feasible region between both the quadratic and my circle. So I would shade just the feasible region. None of this would be shaded because the quadratic does not include it. So my final answer is what they both have in common. And I can get rid of everything else. So this is technically, if I were to get rid of everything else, this is actually called linear programming, which is just a feasible region that they all have in common. So here's a boundary point right here. Here's a boundary point right here. Here's a boundary point right here. Just this shape. It's not a circle. It's not a ellipse. It's just a shape with a feasible region. Okay, let's see if you guys can do the last two of the last one on your own. I got to get new pens because this red sucks. This red is at the end of its lifetime. All right, last one. See if you can graph y. Oh, first off, look at y plus absolute value of x minus 3 is less than 3. I'm going to change that. I'm going to subtract absolute value x minus 3. I'm going to subtract the absolute value of x minus 3 to move it over. This is my first graph I'm going to graph right here. See if you can graph that. Okay, you should have paused the video and seen if you can graph it. So my vertex for this V is 3, 3. This negative means I go down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. And I continue this pattern. All right, I go down 1 over 1, down 1 over 1. And now I'm going to choose a test coordinate. Now look, it looks like it's going to go through 0, 0. I don't know for sure, but I mean, I do know. But let's just say, I don't know, it looks like it. Let's just choose another coordinate that we know that's not in here. Let's choose 0, 2. If I plug a 0 into my x, a 2 into my y, and do the math, I get 2 is less than negative, the absolute value of 0 minus 3 is negative 3. Absolute value of negative 3 is positive 3, but I have that negative in front of it, plus 3. 2 is less than 0. That is not a true statement, so I'm going to shade inside. Because I'm shading away from that. Okay, now the very last one that I'm going to do, which is x is less than y squared. You should know this, since you guys are a STEM class, you should know that this is going to be a function, not a function, this is going to be a graph. X is less than y squared. It's going to look like this. Because if you have x equals y squared, it's going to look like this. Now I got to figure out if I'm going to shade in here or on the other side. Hold on one second. I'm going to use it, let's use this test coordinate of 0 and 2. So if I plug a 2 squared, I get 4. All right, so if you look right here, you should see that 0 and 4, this is not going to be a true statement. 0 is not greater than 4. So I'm not going to include anything in here. So I'm going to shade away from that. But remember, I'm shading down here, but I'm not going to shade until things start overlapping. And once I leave this boundary, I'm not going to shade. I'm not going to shade anywhere else other than where there's intersection. So technically, I don't care about this area at all. All I care about is where the overlapping region is. So on an XY coordinate plane, the feasible region is all right here.